Now we are ready to design sequential circuits. Here is the detailed step-by-step procedure for designing sequential circuits. The very first step, from the given description or specification of the system, we derive a state diagram. If possible, we want to come up with the minimal number of states, which obviously requires less hardware. And then out of the state diagram, we assign binary values to each state. So it's called the binary encoding of states. Then we construct a state table from the state diagram. The next step, we have to choose the type of the flip-flops we are going to use for implementation. So far we have studied D flip-flop, JK flip-flop, and T flip-flop. Depending on the types of the flip-flops, the design procedure is slightly different. Then, from the state table, we derive simplified flip-flop input equations and output equations. Then finally, we draw the logic diagram. So let's apply those procedures for an example problem. The system we are going to design is called the sequence detector. Sequence detector is a system where you have one single input and one single output. The input receives a bit stream. At each clock, you have a clock. On each clock, you receive one bit information, 0 or 1. So in every clock tick, you give a 1 bit information and 1 bit information and so on. What this sequence detector does is that when certain sequence bit pattern is detected, then output becomes 1, otherwise output stays 0. Here, the system we are going to design is a sequence detector where it detects 3 or more consecutive ones. If the system detects 3 or more consecutive ones, then output becomes 1, otherwise output remains 0. So for example, input, if we give the very first time 0 to the input, then output should be 0 because we didn't detect any 3 or more consecutive ones yet. And then on next clock tick, 1 comes into the system, and still we don't have 3 consecutive ones, so output is 0. And then another one comes in, output is still 0. And then another one comes in. Now we have detected 3 consecutive ones, so output becomes 1. Now another one comes in, then still we have 3 consecutive ones, so output becomes 1. And then 0 comes in, then we don't have 3 consecutive ones, so output becomes 0. Again, the 1 comes in, still output is 0. 1 comes in, still output is 0, and so on. So this is the behavior of a sequence detector for 3 or more consecutive ones. Once the problem description is given, the next step is we need to construct a state diagram. A state diagram, you need to first find it out the states, each state, meaning of those states. In doing so, you can actually simulate the system so that you can figure out how many states we need and what is the meaning of each state. So what I mean by simulation is that suppose you were the sequence detector and you are receiving 1 bit information at a time with the clock ticks. And then you are to produce a correct output once you detect 3 consecutive ones. Then what do you need to memorize minimally? What cases you need to memorize minimally? That becomes states. Of course, if you memorize all the inputs, the very beginning it was 0 and then 1 and 1 and 1 and 0 and 1. And if you memorize all of those ones, you can correctly produce output. But if the system is running for a while, then you have received millions of bits, then your memory capacity demands too much, so it's unable to memorize all of those. So instead of memorizing the actual bit stream, if you memorize something different things, then you could possibly handle the same situation. So what do you need to memorize minimally? Instead of memorizing the actual bit stream, you can actually memorize 4 different cases. Whether you have not detected one at all, or so far you have detected only one single one, or so far we have detected 2 consecutive ones. Another case is that we have detected 3 or more consecutive ones. If you simply memorize those 4 different cases, then you can correctly produce output for this sequence detector. So, from the problem description, first thing is find it out how many states do you need and what's the meaning of each state. In doing so, just consider yourself as the system, then what do you need to minimally memorize? To figure that out, then you will find the number of states needed and the meaning of each state. Then out of that definition of a state, then you can construct a state diagram. So we'll state diagram in a circle, you put the name of the state. So we have 4 circles, 4 states. We label them as S0, 1, 2, 3. The beginning with the state 0, which meaning of which is no ones detected yet. Then if 0 comes into the system, then you remain in the same state, no one's detected yet, and then you produce output 0. This is how you construct a state diagram. And when you are in state 0, input could be 1 or 0. So input 0 is taken care of. But if you receive 1 input, then state becomes one single one detected. So you make a transition to state 1, but still you produce output 0. When you are on state 1, if input becomes 0, then you goes back to state 0 where no one's detected and output remains 0. And then when you are on state 1, the input becomes 1 on next clock tick, then you make a transition to state 2. The meaning of state 2 is 2 consecutive ones detected. You still produce output 0, not 3 yet. When you are on state 2, when input becomes 0, then you go back to state 0. You produce output 0. When you are on state 2, and then when you receive 1 input, then you make a transition to state 3. Meaning of state 3 is 3 consecutive ones detected. And then finally you produce output 1. When you are on state 3, when you receive a 0 input, then you make a transition to state 0 and producing output 0. But if you receive a 1 input on state 3, you remain on the same state, 3 or more consecutive ones detected, and then you produce output 1. So we took care of all possible transitions on each state. So this completes the construction of a state diagram. Then you need to convert this state diagram into a state table. State table, state diagram carry exactly the same information but in different format. So you can construct the state table. Here, state table uses not the label of the state but binary number assigned to the state. Since we have 4 states, state 0, state 1, state 2, state 3, then binary encoding naturally would be state 0 means 0, 0, state 1 means 0, 1, and the state 2 means 1, 0, and state 3 means 1, 1. So we have 2 bits for state encoding. And then each bit represents a flip-flop. Remember, flip-flop can memorize one single bit information. So having two flip-flops, you can represent the four possible values. So let's have a flip-flop A and flip-flop B. Flip-flop A represents the first bit, and flip-flop B represents the second bit of a state encoding. Using those encoded state values, we construct a state table from the state diagram. So here, state table is all possible present state value and the inputs. Then what will be the next state and output? So here we had the state diagram. 0, 0 means state 0. When input 0 is applied to the sequence detector, then we remain on the same state 0, 0 while producing output 0. While you are on state 0, when input 1 comes in, then we make the transition to state 1, producing output 0, and so on. So it's a direct translation from the state diagram. We construct a state table. From the state table, now we derive a flip-flop input equation. Here, the example is for D flip-flop. Remember the behavior of a D flip-flop. Whatever is on D will appear on the output of the flip-flop on next clock tick. Remember, those states are stored on a flip-flop. So what this table means is that as to the flip-flop A, currently you have a 0. On next clock tick, flip-flop A will have a 0 value. Currently 0, and it will have a 0 value. And so that's meaning of a next state. So next state is the value on the flip-flop on next clock tick. And D flip-flop, the value on the flip-flop output is the same as a input to the flip-flop. So in D flip-flop, you have a D input and the Q output. The output of the flip-flop is exactly the same as whatever you give on D on next clock tick. So to make this state table, what you need to do is you need to apply on D those values. If you apply those values on input D, that value will appear on Q on next clock tick. So those are desired value to be supplied on D whenever those are current conditions. So currently you have a value of A, value of B, and the input. Then we need to apply those things properly so that which will become something like this on Q. So what it means is that input equation for flip-flop A, input equation for flip-flop A is a function desiring those values with those inputs of the function. In other words, input equation for flip-flop A is a function of A, B, and X. And the value of the function should be those. So we can construct a K-map for input equation flip-flop A, where you have a 3 variable A, B, and X, A, B, and X, and the desired function value is a 0, 0, 0, 1, 0, 1, 0, 1. So 0, 0, 0, 1, 0, 1, 0, 1. So that's the equation for DA. So using K-map, we can find a simplified equation for that. As to the input equation for flip-flop B, given A, B, and X as a variable of the function, we desire those values. so that those values will appear on flip-flop output on next clock tick. So we have a function value 0, 1, 0, 0, 0, 1, 0, 0 based on A and B inputs. So 0, 1, 0, 0, 0, 1, 0, 1. Using K-map, we find the simplified equation for that. For output Y, given A, B, and X, we construct a K-map and then derive a output equation for that. So once we have flip-flop input equations and output equations, altogether they are state equations, we can draw logic diagram. So those equations are derived from the state table in the previous slide. Once the equation is given, you can draw the logic diagram. What this equation means is that input to flip-flop A is all of those two product terms. So input to flip-flop A is all of those two products. A and X, one product, A and X. And another product is B and X. So B and X is another product term. They are all together. So from this equation, you should be able to draw logic diagram. This is for B, and this is for Y. So D flip-flop is designed, system with the D flip-flops are designed this way. But if you are going to use a JK flip-flop, we extend the state table a little bit. So from the same problem, over here we got the state table from the state diagram, but if we are going to use a JK flip-flop for the system, then we need to extend the table for the purpose of deriving a flip-flop input equation. So what this state table means is that currently flip-flop A has this value, but on next clock tick the state flip-flop A should have this value given those other values. That's the meaning of a state table. But we are going to use a JK flip-flop. So if flip-flop A is a JK, flip-flop B is also JK type. Then we know that JK flip-flop has two inputs, and the behavior of a JK flip-flop is such that if J and K are both zeros, then output remains unchanged. And then if JK we have 1 and 0, that output becomes always 1. And output JK is 0, 1, that output becomes 0. If JKs are both 1 and 1s, then you have output complemented, or it's toggled. 0, 0 remains unchanged. So this is the behavior of a JK flip-flop. So on the first entry of the state table, what we have to have is a flip-flop A remains unchanged with a 0 value. Then how do we apply JK input for that? To have output 0 on next clock tick, we will have a 0, 1 as a JK. So 0, 1 is a one choice to make output 0 on next clock tick. Another possibility is that from 0 to 0 on next clock tick is don't change the output. So 0, 0 is another choice for JK input. So overall, we should have a J as a 0, but K, we don't care. It's either 0 or 1 is okay. And for flip-flop B, it should be from 0 to 0. So exactly the same way for flip-flop B, we should apply 0 and don't care. The next entry is also from 0 to 0 for flip-flop A. So 0 and don't care works for that. And for flip-flop B, the 0 becomes a 1 on next clock tick. So to make output 1, we have two choices. First choice is J is 1, and the K is 0, then output becomes 1. Or from 0 to 1 is we can toggle the output. So applying 1 and 1 on JK inputs, then we can toggle the output and produce 1. So JK input for a B flip-flop for this case is 1 and don't care. In this way, you can extend the truth table. So let's pick up a few more cases. Here, for flip-flop B, 1 is the current value, and then next value is a 1 again. So to make from 1 to 1 on next clock tick, the possible inputs for JK is 1 and 1 means we can have a 0 and 0 so that the value remains unchanged. Or we can have a J input 1 and the K input 0. That's another choice. So J input, we don't care. So using those JK flip-flop behavior, we can complete the extension of the state table. Then we can derive an input equation for flip-flops. For JA, we have a K-map. Given A, B, and X, we desire those results. So we construct a K-map utilizing don't care conditions. And then we derive a simplified equation for JA. For KA, given A, B, and X, we desire those values. So we construct a K-map for that. And then we derive a simplified equation for that. So we have a one PI and another PI here. For JB and KB, we do similarly. Here, for convenience, we didn't put output Y. Output Y, it does not depend upon the flip-flop type. So exactly the same equation we can use from D flip-flop. Once we have flip-flop input equations, then we can draw the logic diagram. So this equation means input J on flip-flop A is a B and the X naught. So here is a B and the X naught. Something like that. You can complete the logic diagram of the sequence detector using JK flip-flops. Again, output Y is the same as a D flip-flop design, so this is not given here. Then last case is that if you want to use a T flip-flop instead, then similarly we need to extend the state table. Given state table, then we are going to use a T flip-flops for A and B. Similar to JK flip-flop. So currently A flip-flop has 0 and then a future value on next clock is 0. Then behavior of T flip-flop. When T flip-flop input to T is 0, then output of the T flip-flop on next clock remains unchanged. If T input is 1, and then on next clock tick, output of the flip-flop is complemented. That's why we call it as toggle flip-flop. So to make from 0 to 0, give input 0, remain unchanged. For B flip-flop, 0 to 0, so we give us 0. For a B flip-flop, in this case, from 0 to 1, we need to give a 1 to make it toggle. And from 1 to 0, we give a 1. So we complete the extension of a state table for T flip-flop. Then input equation for flip-flop A, given A and B and X, we desire those results. So we construct a truth table for TA. The given A, B, and X, we desire those values for flip-flop B, so we construct a K-map for input equation for B flip-flop. Simplified equation here. So given those two input equations, you can draw the logic diagram. Of course, here output Y is not given here because it's the same as a D flip-flop case.